Okay, this is the this is the last week, and then we just have 2 more classes to finish the semester. And today we will be able to cover the surface integrals, surface area. And in the last class, I'm just gonna go ahead and then give you the, I think, last chapter of the semester. Now with the Thursday class, actually, hopefully we're gonna be able to finish everything, almost everything. Maybe one thing is gonna be missing. But so seeing right the most of things actually, and then understand the purpose of the learning the multiple calculus. So why do we need multivariable calculus? What purpose can we use for, right? So as you see, there are lots of different areas we could use the multivariable calculus tools, like the partial derivatives, integrals, the double integrals, triple integrals, vectors, vector functions, the surfaces, and line planes. So, but today is gonna be since this is gonna be basically the last topic, and then the all other things I'm gonna show it to you, basically it is gonna be related with this topic. And remember in last class you said that you would extend the due date review when would that extension to due date be? Okay, I think the extension. So of course I'm gonna extend, but the extension still, right? You can still go ahead and then do the review. There's still more time, I know, as far as I know, but no worries about that, since in the web assign there's a weekly assignment tab. That's why, okay, that prevented me to give the more extension, but no worry. Okay, I will extend that one more until the final day. Thank you for reminding me, but it was in my it was on my mind, and you don't need to worry. I'm going to extend that one. I hope you used the extension for the last quiz. Yeah, since as far as since it was because of the Thanksgiving, I didn't actually close the quiz 9 on last Tuesday. I extended until Saturday midnight, but I saw there are a lot of actually friends around. They wanted me to extend, and then I extended until Sunday midnight. I hope you benefited from that one. All right, the surface integral problem is gonna be similar to the line integral problem. Look at the name, surface and integral, right? Like the line plus integral. So the surface integral problem is kind of the line integral problems, and we are gonna try to define this integral over a surface, all right, as the name suggests, like we did for the line integrals. Let me go ahead and review the line integral part for you, okay? And then you will understand more if you remember, okay, what I did for the line integral, since the connection between the line integrals and the surface integral is gonna be, okay, obvious, similar, and then it inspires us, okay, to understand the surface integral. So look at what we did for the line integrals, guys. Line integrals. All right, I had a curve in this space, something like this. What I did, I tried to use my Riemann sum right over this curve, and there was a function going through something like that, but I chose this curve along the way of this curve. I tried to take the integral of this function, and I noticed that this integral actually gave me the surface area of the whatever I have below that function, kind of curtain. Look at that. This is a curtain. That's the surface area of a curtain, right? So this is my C, this is my F, and the line integral gave me, right, the surface area along the way of this curve. And later I noticed that I need to go ahead and then give the parameterization for my curve R of T, which the component form of the, right, that representation was like this. And I noticed that, right, that this integral could also be calculated using, right, this formula after using the, right, the representation of the curve parametrically. I hope you still remember all of these things. All right, that was how we defined, right, the line integrals for the scalar function, just scalar function. But later, right, we went ahead and then we defined the line integral for the vector field. We defined the line integral for vector field, as well as we saw, right, the fundamental theorem for line integrals, and also the Green theorem. And related with the Green theorem, right, we defined curl and then divergence concepts. Okay, this is all actually what we have learned with the line integral. And then we saw if you define the line integral over the vector field, it was equal to the right work done in physics. So, but it might be, right, there's some other, right, the physical correspondence in your related problems. The interpretation of, right, this line integral could differ based on, okay, what field you are in, based on what application you are doing. But it teaches us a lot, right? Especially the particle in the, right, the vector field, the motion of the particles under vector field. Actually, there are a lot of, right, the different interpretation in physics. Today, similar to what we did the line integrals, look at it. If I'd like to go ahead and then define the surface integral. Surface integrals. Similar to what I did, okay, for the line integrals. Look at it. Let me show it to you what I mean, what I'm gonna mean actually by surface integrals. Let's say I have a surface around. You see, kind of something like this. This is my surface, okay? Maybe I can do better shape. Yeah, let's do like a rock. Okay, this is your surface. What I like to do, I'd like to use this surface and then, okay, make small pieces override the surface and then define the integral over the surface. So that is going to be my purpose, okay, for the last two classes. And then, of course, we are going to deal with the results of this discussion as well. So if you, after defining the surface integral, it is going to help us to solve many, many problems. Like what? Like, for example, okay, since we are going to define the surface integral for a scalar field, like we did the integral, line integral, scalar field, and a vector field. Okay, we will go ahead and then do the same thing, okay, for the surface integral. Then we are going to see, okay, the similar theorem, okay, for the surfaces, like we saw, right, the Green theorem for the line integrals. It's going to be Stokes theorem. Stokes theorem is going to be just the, okay, expansion of a Green theorem or the fundamental theorem of calculus, like the line integrals. The surface integral will help us, okay, to understand the a surface is under a vector field. What do I mean? Think about, like, okay, you have a surface that might be the sphere, that might be, okay, cone, that might be, these are the similar actually surfaces we know. The paraboloid, the cylinder, okay, you see all of these shapes right around in the real world. If you want to, for example, if you want to understand the behavior of all these surfaces. It might be, of course, different surfaces under a vector field. What type of vector field? Like the heat field, right? Like the pressure field, like the magnetism, right? Like the electric field. So if you want to understand, let's say, right, look at that. I want to put right this surface under such a vector field, you see? We saw some application. This might be right, some force field. So what happens, right, to these surfaces? Or if it is right, this, if it is the heat field, right? These might be right the heat waves. We can think about. Okay, how could the right the heat dissipate over the surface, for example? If you are wondering about, okay, I'm not sure you are not wondering, but you might wonder, okay, later, if you are wondering about all these type of questions, the surface integral actually will help you, will tell you something. So what would happen to your surface under this fluid, under this flow of, right, the vector field? All right. So these are the questions surface integral will help us to understand more. This is just the introduction, all right? This is just the introduction about what we are going to do. So I want you to understand basically everything and how we are going to use the surface integral, okay? Whatever I have said so far, okay, that was just the introduction about the surface integral. Why do I need the surface integral? And then how could I construct the surface integral using, right, the idea similar to the line integral? All right. Now, okay, now we are aware of the, right, the need of the surface integral. We need surface integral, but the problem is, okay, you can ask, okay, you can ask this question: what's the surface integral, right? What's the surface integral? Then I should go ahead and then define the surface integral. To define the surface integral, I'm going to start soon, okay? Before the surface integral, actually, we need to define a couple different concepts. But before starting to get into this discussion, I want to remind you one more thing, okay? Then we are going to start. Remember, the discussion of the line integral, right? It came from actually the normal integral. You remember? I always took my integral in this interval, right? That was just the usual integral, guys. You had a function and then you were trying to implement the right area problem. And then you were given, right, this idea, f dx. You see, dx is just the x-axis, straight line, straight line. And then there's just one way. And then it is just an interval. That is why how you define it. Now look at that. C is a curve. This time you have, right, the many direction. That's why you can't just use the dx, right? That is why we use the parameterization, right, to simplify the process. Similar to the, look at that, this idea. This idea leads to the right line integral. Now I want to remind you how I define the right. I define the double integral, right, over region. If you remember, that was the region. What we did, right, we divided this region. We made a grid, and then we used, right, rectangular areas, right, over a function, right. That was the function. That was a surface as well. And then over a function, look at that. We used the rectangular prism to find the. But basically, we did this, right. That was the integral. But now, if I want to define the surface integral, look at this time, I'm just going to have the S instead of D, right? That the D is going to become, since I want to define my integral over this surface. And then this surface is not like, right, is not like the D, since I can grid the D, and then D could give me some rectangles. Look at that. If I want to make a grid over S, these are not rectangles, right? These are not rectangles. But still, I could use the similar idea, what I did here, right? What I did here. One more thing to add. Remember the discussion we did for the double integrals. If you choose the f is equal 1, that would lead what? That would lead? Huh? Any answer to this question?
The area.
Exactly, perfect. That would give you the area of D, right? Independent from the actual function f. So I could use the same idea for the surface area problem as well, okay, after defining the surface and then integrals. All right, now we can now start, guys, okay? First, how we can define the surface integrals. But to define it, I'm gonna use the same approach how I define the line integral. To define the line integral, you remember, I always use the curve and then parametric curve, right? I found the parameterization for my curves. Curves gave me actually a mapping idea. Huh? So that was the parameterization I did my for curve, and then look at that. I mapped to any point, right, in this interval to the curve. That's the curve, by the way, right? And then this is the point, for example, AB. So for T is T1, you chose here. So this is X T1, and then this is Y T1. Like I said, right, we use the parameterization to find out, right, the line integral. Otherwise, that wouldn't be easier. Similar to that discussion now, guys, I'm just gonna go ahead and then use the parameterization for the surface integral. Surfaces, right? Surfaces, or you can just write it here, you say this is the curve parameterization. And then this is surface parameterization, which I'm gonna need for my surface integral. What I will do, look at this time, guys, I'm gonna find out, right, the mapping for the surfaces. Using one variable actually will not be fine to define, okay? To define the surface. What I need two parameters, U and V. One of them, okay, will be representing, right, one of the axis, the other one represent the other axis. So, and then I'm gonna define, right, the old axis with respect to U and V. And then this is gonna be kind of the parameterization I'm gonna using for the surfaces. What I mean here, guys, look at that. I had the UV plane. I'm mapping, right? I'm mapping, look at this interval over the surface, all right? So look at the similarity between the, right, the curve parameterization and the, right, the surface parameterization. In the curve parameterization, I just needed one parameter, but look at this time, I'm gonna need, right, the two parameters, right? The two parameters can define a curve. And then these are just the transfer. Let me give you the official definition of the parametric surfaces. Definition. Given a parameterization of surface RUV which is given this way, the parametric domain of the parameterization is the set of points in the UV plane. In the UV plane that can be substituted into R. all right, inter. What it basically says, the domain of, right, the R is gonna be, right, the UV domain. The UV points, right, you can use in R. If you can't use, you can take them. And then you just need to produce all these, right, the points to get the surfaces. That's all we need, basically. All right, now let's go ahead and solve some examples. What do I mean by the examples? Before example, I also want to remind you, since as you see, right, that to discuss all these methods, we refer to the past, right, a lot, since we need to use a lot of, right, the old concepts we learned during this class. I hope you still remember what this is. What is this?
It a cylinder?
Cylinder? Or what is this? Or what is this one? Do you still remember all these?
I believe the second one is a sphere.
Which one?
The second one, the one in the middle.
I think the sphere is the third one. And this one is cone. And this one is paraboloid. I hope still you remember, right, that these surfaces, right, that we learned their equation by just looking at the, right, the variable powers and the variable sign, right? At that time, we were using that type of technique. And then we draw them, right? A couple months ago, we learned how to draw them. But today, look at, these are all surfaces, guys. I'd like to go ahead and then give the some parameterization, okay, to represent the same equation, like this one. Let me give you an example. Describe the surfaces. Describe the surface as parameterized by RUV cosine u, sine u, and v. And u is in this interval, and then v, you can use this notation, guys, in this interval. So what I want you to do, of course, we are going to do together for the first one. I want to find out an equation for this parameterization. Look at, this is the parameterization, right? Parameterization. How am I going to find, right, an equation for the surface, the Cartesian equation? If you look at carefully, these are, right, the components of the surfaces. So I should do something so that I could eliminate the u and v parameter, guys. Why am I trying to eliminate them? Since to give an equation like here, look at it, you need to relate the x, y, z variables, correct? That's what I'm gonna do. All right, the question is now, how could I relate the x and y and then z, eliminating, right, the u and v? Do you have an idea? What I could do, if you see the cosine and then sine, you can use this trigonometric identity. I have, look at that. I have this relationship. Cosine u square u plus sine square u, which is equal 1. I know that. Cosine u is equal x. Sine u is equal y. And then, as you see, now I eliminated the u parameter, and then now I have, right, this equation. But still for the z is equal v, I have this question, right? Can I relate the z by x and y? Can I, right, eliminate the v variable, v parameter? Is there a way? there is no way to relate to okay, z and then x and y in this case, guys. So that is all. That is all I can do. I can just leave at this point. Now I can ask, what is this? What is this? What is this? So what type of surface is this? How could you find out what is this? If you don't know anything about the surface, I would do this, guys. Keep z constant. So just assign the value, right, to the z, like the 1, 2, 3, 4 million, billion. Okay, doesn't matter. If I assign the constant to the z, for any constant of z value, I would always get x squared plus y squared, which is equal to 1. What is that? A circle, right? So for any level of z, you have a circle. Same circle? Yes, same circle, right? Why? Since the circle, look at the radius is always 1. Then I would keep the x and y constant. If an x and y constant z, right, it changed by v value. That means what is that? That is line equation, right? That's the line equation. So let me show it to you, okay? The picture. So we could understand what's going on here. Look at guys. This is the shape you're gonna get at the end of the day. The first part is xy constant. You see? X and y are constant values, and what z right is increasing or decreasing by v value. But look at here. These are all right, the circle, their radius is 1, z constant here. So to get right the better picture, you need to combine right the both. As you see, this is what? A cylinder. This is a cylinder. Does that make sense? Do you have any question?
Can you scroll up a lot?
Any question, guys? All right, what I have done here, as you see, I had a parametric equation, right? Like this one, like R, and then it gave me a normal equation, right? The normal Cartesian equation. And then that's how I knew, okay, what it is. One more question, let's solve, right? One more question. Describe the surface as parameterized by this vector equation, this vector function. This time, it is a little bit different than the previous one. Look at guys. Okay. And then u is between infinite 0. Since v is angle, right, it is going to be between 0 to pi. Can you please relate x, y, z, and then find an equation for this surface? Exactly, Charles, that's correct. Can you, would you like to say what it is? What surface is that? What is the shape of that surface? So as I did right there in the previous example, look at that x, y, and z. X equal u cosine v, y is equal u sine v, and then you can relate right to these two using this trigonometric equation, which is going to be equal u squared cosine squared v plus u squared sine squared v. And then that's going to be equal u squared, since when you add right the sine cosine, it's going to be equal 1. But I have another thing here, as you see, right, that the third parameter, the third actually variable is equal u squared, which is z. So this operation then will be equal to z. At the end of the day, look at this parameterization will give me what? Z is equal x squared plus y squared. So what is this? This is elliptic paraboloid, right? Something like that. Something like that, guys. Okay. Any question? Are we good? One more example. This time, I'm asking the other way around. Give a parameterization. Give a parameterization of the cone. Cone, which normally it is given by this equation, right? Lying on or above the plane z is equal -5. So this time look at that. You need to give me right the parameterization. I gave you the equation and you need to give me the parameterization, guys. Can I use the similar parameterization I used for the previous example? Why not? Whenever you see the x squared use y squared, you need to know, right, that there's a circle there. If you have the circle, you can always use this parameterization, u cosine v, y is equal v, u cosine sine v. Did you see? All right. And I can relate these using the same geometric formula. And then that's going to be equal u squared. And then that is equal, right, from here. I know that this is equal z squared. So u squared is going to be equal z squared. Did I find something, right, the parameterized for z? Yes. As you see, z is equal u. And then I found, right, the parametric relationship for the x and y, z. And then that's how I'm going to give the parameterization, u cosine v and u sine v and just u. But the one more thing, it was saying, right, this surface is lying on or above the plane z. Since z is equal u, I'm going to give the domain of u this way. It should be bigger than -5 or equal. And then v is the angle, that's why it is going to be between 0 and 2 pi. Right? That condition at the end of the equation, actually, it just puts me in this interval for u variable. I hope you got the idea for the parameterization. So that's the first step actually on the way to the surface integral. So first, thank you, Mikhaila. First, I need to understand how I can find a parameterization for the surfaces, okay? Now, in the second part of this class, we are gonna go ahead and then define the surface area problem, guys. That's gonna be the second step, okay, on the way to the surface integral. And then finally on Thursday, we are gonna define the surface integral for the scalar field and the vector field. As I mentioned, okay, at the beginning of the class, then it will lead to the Stokes theorem, which is kind of right the Green theorem in line integral. All right, let's give a short break, and then we are gonna come back soon for the second part. Are we still recording? I forgot to stop, guys. All right. So just give me 1 second. So I need a couple. Picture here. Okay. So now we are gonna go ahead and then discuss the surface area problem, guys. Surface area of a parametric surface. Surface area of a parametric surface. So what I want to do, I want to find out the area of the surface given here, guys. You see? If you would like to find out the surface area, here you see one of the examples. But this might be any surface around you have. You see, right? Any look at this one. Look at this glass, right? Even this one has a surface. It is kind of what? This is cone, right? But it is. I'm not sure if you. Yeah, why this happens? So anyway, you know, right, that these kind of glasses, like the coffee glasses from Dunkin' Donuts or the similar coffee shops. So this is kind of cone, actually. Why? Since you cut, right, you use the two cuts, right, from the bottom and from the top to get that cone. So if you want to find out, right, the surface area of this one, since you need it, you are going to need why? You are going to look at the Dunkin' Donuts, right, maybe million, right, the glasses like this one. The manufacturer of this glass actually needs to spend the material to produce this glass, and then they need to find out, right, the surface area. Since they are gonna spend some money, they need, right, the surface area. And then you see a lot of different shapes right around, like this glass, like the sphere, like the cylinder. There are lots of different shapes. There is another one. Look at that. Look, this one. You see. But this is not kind of look at the surface. We know, actually, we are aware of the surface. It is kind of, right, a combination of two different surfaces, right? Even I still need to, right, calculate the surface area, and then maybe later the volume, right, to calculate how much materials I'm gonna be using, right, to produce this one. So all of, right, the similar idea you can use for the materials around you. All the manufacturers actually use kind of math, okay, to get some idea about, right, how much materials they're going to use, how much they're going to spend. This is just one of the simplest example, okay, we can use the surface area problem. Okay, then if we need, right, to for this type of, right, the problems, if I need to find out the surface area, I'm asking this question, right? How can I formulate finding the surface area problem? Okay, so look at this one. Look at this, right? The small piece of, right, the big surfaces. The small piece SIG, I sub-index, right? That small part of S, and then the area of, let's say, okay, the area of the SIG is equal to delta SIG, delta SIG. So as you see, there is a grid here, right? There is a grid for each SIG, I can go ahead and then add all of those S delta SIG, the area of the right, those grid pieces, that's grid pieces. And then as you know, there is M and then N times SIG pieces. If you would like to find out, right, the surface of this S, as you know, you need to use, right, the infinitely many, right, the grid pieces, infinitely many. When you say infinitely many, as you know, right, you need to take the limit. And then that will give you, right, the area of S, right? That's the idea we always use. But the problem comes from this, guys. Comes from this part. What is the area of the delta SIJ, right? So the area of SIJ. How can I calculate, right, the area of SIJ? When I did this for the right, the region D on the plane, I used the rectangles. You remember? I just mentioned at the beginning when I discussed about, right, why do we need, right, the surface integral, I discussed the double integral. You remember, right, that you need to grid the region D using the rectangles. And since you know the rectangle areas, you can use rectangle areas to calculate the region D. But now, as you see, guys, this area is not going to be rectangular most of the time. So you see this area, right, whatever it is, right, it is not going to be rectangle. Since it is on the surface, right, it has some slope depending on what it is. It is not kind of, right, the rectangle. But can you please tell me what other shape it looks like? Instead of rectangle, what other shape it looks like? Since the answer will determine what I will do, how I will define the surface integral. Huh? Can you, for example, can you say, okay, there's an answer, let me see. Well, sorry, caps. What do you mean, Bailey? Caps. Okay, does it look like the parallelogram? Huh? Either a yes, correct, Bailey. Does it look like the parallelogram? Huh? It looks like the parallelogram, you see? It looks like the parallelogram. I could try, right, using the parallelogram for this shape. Okay, then if it looks like the parallelogram, the question turns out this. Do I know how to calculate the parallelogram area? Have you seen such a thing in this class? Calculating the parallelogram area? Huh? Do you remember something like that? So I know it seemed at that time, yes, Bailey. I know it seemed that time, right? Why do we learn the parallelogram area? Well, look at now. We need it now. We needed to use the parallelogram area to calculate the surface area, guys. Okay, exactly, Bailey. Thank you. Cross product of x. Okay, let me remind you one more time. If you want to calculate the parallelogram area, just give me 1 second. Okay, you need a 2 vector. And look at that. This parallelogram area can be calculated using, right, the cross product length between 2 vectors. That was the formula we used to calculate the parallelogram area. All right. What can I do now? Look at now this shape, guys. To calculate the parallelogram area of that Sij, I need 2 vectors. All right. How am I going to find those 2 vectors? Hold on, where are you going? I don't know why it is so slow. Okay, just stop there. So let's say this is again Sij, or you might assume, okay, you might assume this is the part of the right S, and then this part, guys, this part is Sij. This part is Sij. You see, the point, the P point is the corner of that Sij, and then the tangent line, tangent vectors, right, at that point, I could use, right? I could use those tangent vectors at that point as a vectors to get the parallelogram area. If I had these tangent vectors, right, I could use to look at that, the cross product of these vectors, right, to calculate the Sig parallelogram area. All right. So there's no other actual vectors I could use, and then that's gonna be, so since this plane, these tangent vectors are gonna be part of the plane, right? The passing through that Sij, and then this parallelogram. Look at that. This parallelogram actually still, it is not right exactly the area you have, right? For example, underneath. Look at that. This is underneath area Sij. It is approximate to this area. Maybe you might say that. One more thing I'm gonna do, okay, for the purpose of my integral. As you know, right, that this surface is the mapping between the UV plane, right, to this one. As you see, this orange line, right, was mapped to this orange curve, and then this blue curve, if it is blue curve was mapped right to this blue curve. So if you take the rectangle here, the delta U and then delta V, let me think, okay, I'm just gonna map this, okay, onto this Sij. To actually get the same scale, I'm not just gonna use the TU and then TV vector. I'm gonna multiply these vectors by, look at that. These numbers, these are scalar, right? These are just length. Look at that. These are just length. These are vectors. I'm gonna multiply these two vectors by delta U and then delta V just to scale. Okay. Still, it is gonna give me a parallelogram, but it is gonna be scaled parallelogram this time. Okay, doesn't matter. But for my integral purpose, it is gonna be perfect idea. Why? Since at the end of the day, look at that. This is gonna. So I could just take these out, since those are just the scalar. Did you see? This is equal what? This is equal, not equal actually. It is approximate to your delta Sij, Aj, the area on the surface. It is of course still the parallelogram area, but it is approximate to delta Sij. Do you have any question up to this point? Is everything clear? Huh? Would you like to give me some feedback? Thank you, Katie. What about others? Just Katie, Bailey, thank you. All right. Thank you, Matt. If you have any question, you can ask. Okay, now look at that, guys. As you know, what I want to do, I want to use infinitely many delta Sij to find out. You remember, right? That I use this limit to get the area, exact area of S surface. So now look at that. If I use infinitely many delta S, the surface area of S will be equal, look at that, will be equal to Tu times Tv, and then delta U will become du, delta V become dV, and then over the region D, guys. Okay, now I got a formula for the surface area. Did you see that? That is how I'm gonna calculate. The surface area. Let me give you the official definition now. This is how I derive the surface area formula. But of course, I need to give a definition for the surface area after this discussion. Then we are going to go ahead and solve some examples, some problems. R UV, X UV, Y UV, and Z UV, which is the parameterization of your surface with parameter D be a smooth parameterization of surface S. The surface area of S is integral D and Tu times Tv dA, where Tu is equal, right, the derivative of all the variables with respect to U, and Tv is equal to the derivative of all the variables with respect to V, guys. All right. Now we are ready to solve some examples. The first example is this one. Find the surface area of the part of the plane with the vector equation below. So that's the vector equation is this one. 2u minus v and 5 minus u and 1 plus 2u minus 3v. U is between 1 and 2, and v is between 0 and 2. All right, what am I gonna do? I'm gonna find first Tu and Tv vector, right? How? Taking the derivative of R vector function with respect to U and V. The derivative of R vector with respect to U, which is equal, look at that. The first component derivative with respect to U is equal to -1 and also 2, right? And the derivative of R with respect to V, the derivative -1, 0, and also -3. Okay. The second step, I need to find out the cross product and then length of it. How am I going to find the cross product? First, let me find the cross product. I hope still you remember the matrix calculation for the cross product. 2, -1, 2. Sorry, my bad. First, I need to put the right ijk. Ijk goes to the first row, and then U goes to the second row. V goes to the third row. If I calculate this, that would be, you need to cross out, right, the first line, first row in the first column, 3, which is 3. And this one, -6, -2, 8, right? And 0, -1, correct? So I think it's gonna be -8. 3, sorry, -6.
Professor, can you go over the J part again?
Yes, let's do the J part again. 2 times -3, which is -6. 2 times -2, this. And then I also have the negative here, right? Which is gonna be -4 plus 4. All right, that's the correct one. Okay. What I need now, is length. Of course, you need to put right this length notation everywhere. How am I going to calculate the length? 3 squared, 4 squared, plus 1 squared, which is equal 16, 25, 26. All right. And then the last thing I'm going to do, TU, TV, DU, DV, and then domain. I already calculated this part, which is equal square root 26 du dv. And then the intervals, look at that. 1 to the 2, the u comes first, the other one 0 to the 2. If you calculate the first integral, 26u 0, 1, 2, which is still equal 26 dv. And then that's going to be equal to 26. That is the surface area, right? Under consideration. Surface area for the plane under consideration. You see, I didn't use, right, the normal plane equation. I just used the parameterization and then formula for the surface area. Any question? One more example, and that's the last question for today. Can you prove the sphere surface area? Sphere's surface area is equal 4 pi r squared. I know you have seen this, right, the formula in many places when you study some, right, geometry, some other things, right, at high school or some other places in memory cards. But now it is time to prove it. Why it is equal, right? Why it is equal 4 pi r squared. Now, you are going to see, okay, why it is equal to 4 pi r squared. But first, you might want to try it. You might want to try and then prove on your own. As you know, first step is to find a parameterization for the sphere. Is to find a parameterization for the sphere. Do you know any parameterization for this? Have you seen such a thing before?
Yes, in the spherical coordinate system.
Exactly, Charles. Great. Thank you so much. In spherical coordinate system, we found a parameterization for sphere. There we use the theta and phi, right? Instead of u and v, If you don't like the theta and phi, you are free to use u and v, guys. It's up to you. But since we use the theta and phi, I'm just gonna give you this hint, but the rest still you can work on this part. That was the parameterization: cosine theta, sine phi, or sine theta, sine phi, and the third variable we had this one. This is the parameterization we use for the sphere, guys. Go ahead and then use this and then use the surface area formula and find the surface area. Work on this a couple minutes. All right. So what I did, I took the derivative of t with respect to t with respect to phi. We can go ahead and then use the partial derivatives here, right? And then took the derivatives and then create these two vectors. Then I am gonna multiply them using the cross product. As you know, I need, right, this cross product multiplication. And now I'm ready to take, right, the S length. For length, I will go ahead and then take the square of those terms, cosine square theta, sine to the 4 phi plus r to the 4 sine square t, sine for phi plus r to the 4 sine square phi cosine square phi. Everything is in square root. What you see here, look at the cosine square theta, sine square theta, right? That's gonna give me 1. Then I have left by R4 sine for phi plus R4 r to the 4 sine square phi cosine square phi. R to the 4 terms and then sine square phi terms are common terms. R to the 4 sine square phi sine square phi plus cosine square phi. You see, this is also 1. And then you can just cancel right to the square root. You are going to have left by r squared sine phi. Since sine phi is between pi and 0, and then sine phi is always right bigger than 0 or the 0, okay, in this interval. That is why you can take this out, right, without absolute value. All right, this is my what? This is my length of this vector, theta times t phi. The next step is this. The theta, the phi, and 0 to the 2 pi, 0 to the pi, r squared sine phi d phi d theta. I used, right, the phi boundaries first. That's why I used the d phi first. All right. Let me go ahead and then take the interval 0 to pi. So it's going to be negative cosine phi times r squared 0 to the pi, and now d theta. If I use right the pi, it is going to be 1, and then negative 1. Sine phi, all right. It should give me 2 square here, 2 square, and then d theta. Then if I take another integral, 2r squared theta, 0 to pi, guys, it is gonna give me, look at that, 4 pi r squared at the end of the day, right? That's the surface area of sphere. As you see, I proved, right, the sphere surface area formula using, right, the formula I derived. Actually, I derived the formula and then I use that formula, right, to show the surface area of sphere. All right. That is all I'd like to share, but don't leave, please, since I'd like to share a couple of things about York rates issues before I stop today. So I haven't sent the weekly email this week, but I'm gonna do it today, last time. You have the last homework and then last quiz this weekend. Those are gonna be the last assignments. And I hope you use the extension for the homework quiz 9. Because of the Thanksgiving, I already extended until Saturday midnight. Normally it was due to Tuesday midnight last week, but I hope you used that extension because of Thanksgiving break. Some of your friends actually asked me to extend more, and I already did that extension until Sunday midnight. I'm hoping, right, you are fine with it. But if you still have some problem having the quiz 9, still I could help you. Okay, that's the first thing. Still I could help you if it is understandable, since that was the Thanksgiving weekend. Please don't go if you are planning to. Don't go, since I'm gonna share a couple of things. You might want to hear that. And second things about the grades, whatever you see on WebAssign, okay, those are now your final grade. There was an issue, okay, this semester, since WebAssign tried to connect the WebAssign and then migrate on my course, but they couldn't do a good job. That's why I didn't move any grades, okay, from WebAssign to the my course. I normally move to the everything my course, but when you see the grades on WebAssign, everything is correct now, and then everything is scaled as in the syllabus. So those are your correct grades, guys. If you have any problem with your grades, if you have some object, if you think, okay, there is a mistake, or if you want to fix any grade because of the problem WebAssign, okay, calls, like the decimal, like the notation, I helped a lot of your friends, okay, in the past. Please let me know so that I could help you to fix those problems. At least you can have, okay, a couple points here and there, okay, to boost your grades. There are some opportunities you can use to boost your grades. First, I'm gonna drop the 2 quizzes and then 1 homework as I promised in my syllabus, okay? Those are gonna be, I'm gonna drop them. Those are gonna be dropped. The second thing, normally I wasn't doing this way, but since I promised to some of your friends this semester, those are the students actually, they missed their exam, some of the exam during the semester, even though they haven't provided any official document to prove why they missed it. I promised them, okay, I could replace their final grade by the lowest exam grade. Actually, I promised to taking the average, but now what I'm gonna do to make a fair grading for everyone, I'm gonna change your final grade, okay, with your lowest exam grade, guys. All right, if the final is better, of course, okay. So final grade will be changed by your lowest exam grades, but you should be aware of that. The final is cumulative, right? It is gonna include all the topics you have learned. The third thing, if there is any homework, not the quiz. If there is any homework you missed so far, if you haven't done, just let me know, okay? So I'm gonna open them for you, okay? So that you can do them, but there's gonna be trade-off. I'm just gonna take some grade off, 15%, 20%, 10%, depending on, okay, when I assign them. So just let me know if you wanna do one of your missed homework assignments, guys. All right. I think we have done maybe 10 homework so far, and then there's gonna be the last one this week. If you have missed any of them, just let me know by email so that I could help you about those. So these are the some, okay, boosting for your grades. If you feel, okay, you don't have a good grade for this Master, can you re-explain what you mean about the final? Is the final being replaced with the lowest exam? Yes. Of course, the final is gonna be, no, I'm gonna replace the lowest exam grade by your final exam. All right? If your final exam is better, right, I'm gonna replace it by one of your lowest exam. Do exam reviews count as homework? Yes, Charles. And then I'm gonna extend that one. That's gonna be another homework since you have a lot of plenty of time, okay, for this one. So, and then it is gonna help you actually learn the materials, right? Since as you see, some of the materials actually requires more work, guys. And then it is gonna help you basically. It should be a requirement, otherwise, I know, okay, some of you will not complete. If you complete to write the review for the final, at least it's gonna help you to prepare you for the final exam. That is why, okay, I wanna make it required assignment so that please complete it. It is gonna be your advantage. Do you have any other question? I'm here and then I can explain or I can answer to any of your questions related with the exam or your grades. Okay, thank you, Mikhaila, thank you, Caleb. If you have any question, is the final exam on the day listed? Yes, Katie, it is gonna be on the day. Of course, I'm gonna email you about the exam as well, but that's the correct day. And then it is gonna be like the normal exam, okay, we did here. The only difference is gonna be, we are gonna have more students here. It is gonna be almost 110 students, okay? Since I have 3 sections. So we are gonna be all together having the exam. All right, guys, see you on Thursday, which it is gonna be our last class, okay? If you still have any question, just stay here so I can help you. Otherwise, have a nice day. See you.
Thank you,
Thank you,
Professor. Have a good
Professor.
day.
Have a good
guys.
day.
You too.